This week we're talking about chemical reactions and the conservation of mass and how that can be shown in chemical reactions. So I apologize ahead of time, my voice is a little bit off because I've been feeling a little bad, but we'll get through it anyway. So let's start out with the ways that we can know whether or not a chemical reaction has happened. So you guys have learned about chemical and physical changes before, and you've probably seen some of these signs described before. But one of the ways we can know that a chemical reaction is happening is if the reaction has bubbles in it after you mix two things together. Those bubbles mean that it's forming a gas. So I have a picture here to kind of represent that. We've got a clear liquid and some white solid, and when you mix them together in the same test tube, you get this bubbling looking thing right here where it's kind of moving upward out of the solution. That shows you that the reaction has gas forming inside of it, and gases like to expand, so they're spreading out to move out the top of the test tube. So that's always a sign when you didn't do anything to cause it to bubble, like heat it up, that there is a reaction going on. Okay. Another one is if you have a color change. So yellow liquid and a clear liquid mixed together, and you see how this liquid is kind of turning red here. It'll eventually spread out and the whole liquid will be more reddish. That is an example of a color change. There's lots of different colors that things could turn, and it depends on what two things you mixed. Another sign is if you just have two room temperature things, or more than one room temperature thing, and you mix them together, and all of a sudden the temperature starts going up. So this picture just kind of represents that. Because there is a thermometer, it shows that the temperature is either increasing or decreasing. Some things when you mix them together it'll get colder, and some things will get hotter. Lastly, if you see precipitation, that's a really good indicator that a reaction is happening, because that means that a solid is forming. So this is like if you have a liquid here and you're dropping a liquid in, so there's a little dropper there. So they add drops of liquid to this other liquid, and all of a sudden this red cloud looking stuff is forming. Eventually it'll all settle on the bottom and look more like this, and this is a solid that has fallen to the bottom of the test tube, and the same thing is true over here. But for the most part, when this happens, the solution just looks cloudy for a while, because these particles are really small and it takes a long time for them to move to the bottom. But if your solution goes from clear, where you can see through it, to cloudy, that means that precipitation has happened. Okay. Now, a lot of you guys will say that the difference between chemical and physical changes is that chemical changes can't be reversed, but that's actually not true, and most people don't learn that until they get to chemistry. Chemical reactions can be reversed, so they are reversible most of the time. Sometimes it would be really, really difficult to make it go back, but most reactions have a forward and reverse reaction. So the forward reaction of what we have here is called photosynthesis, where you have the plant taking carbon dioxide and the water that the plant drinks, and it makes its own sugars, and it produces oxygen for us to breathe, like we know that about trees, right? And this requires some energy, so that energy comes from the sun, because this direction is a little bit more difficult. The reverse, though, is where we come in. When we eat sugar and we breathe oxygen, we produce water and carbon dioxide, and we breathe out that carbon dioxide, and our whole body has lots of water in it, so I don't really know where that water goes. But that produces energy for our bodies when we do that process. That's the energy we get out of sugar. And so this reaction goes in both directions, and it's actually exactly the same reaction. It is a chemical change, because carbon dioxide and water are not the same substances as sugar and oxygen. Okay, either way, either reaction is possible as long as energy and matter are conserved in the universe. So in this direction, energy was taken from an outside source to allow the reaction to happen. And we have the same amount of carbons, oxygens, and hydrogens on the left side of the reaction as we do on the right side. And the same thing is true when we go in the other direction. Instead of energy coming from somewhere else, this direction, the energy is released out, and that's why we see energy coming out. So both are possible. Okay, now when you read a chemical reaction, it's important for you to know what you're reading. And I know that chemistry looks like a foreign language to a lot of us because we've never really looked at this before. So I want to break it down. An element is anything that comes off of the periodic table. It's a fundamental part of matter. That means that it's one of the smallest pieces of matter, and it's unique from all the other elements. And they usually start with a capital letter. Some of them are just one letter, like oxygen, but some of them are two letters, like sodium, Na. Each of these are used to build bigger things called compounds because elements are kind of like Legos, and they go together in certain ways to make bigger compounds. So an example of a compound, since I wrote this in blue, I circled it in blue, is Na2O. There are two sodiums in this compound and one oxygen, and they're all put together like pieces of a Legos. They're combined or bonded, we're going to learn about bonding later, elements in one unique substance. So Na2O is different from H2O or any other kind of compound. Alright, subscripts. Subscripts are these little numbers at the bottom, so I highlighted them in green. They mean how many atom or element is in the compound. Sorry, I didn't say that right. How many of each element are in the compound. So there are two sodiums, that's why there's a little 2 after the sodium. And in oxygen gas, there are two oxygen atoms, and that's why there's a 2 after the oxygen. Alright, coefficients. These are the numbers that come in front of an element or a compound in the reaction, and these tell you how many of that compound or element is needed in order for mass to be conserved overall. So what I mean is, this, if we cut the reaction in half right here, this is like the halfway point. On this side, we have 2 sodium atoms just because there's a 2 here. This is the coefficient. There are also 2 oxygen atoms. We have a problem here because I did not balance this correctly. I should have looked at that a little more in depth. There are 2 sodiums here and only 1 oxygen. So if there are 2 oxygens before the reaction and only 1 after the reaction, then mass is not conserved. So I would actually have to balance this differently. I would have to put a 2 in front of this to get 2 oxygens. But then that would also give me 4 sodiums. So instead of putting a 2 for my coefficient over here, I'd have to put a 4. So sorry, I didn't balance the reaction. I was making this quickly. Alright, last thing here. Reaction arrow. This shows the direction of the reaction, and it separates out the reactants from the product. So anything that is before the reaction, the left side, we would call reactants, because they're the things that are going to react with one another. And anything after the arrow we call the products, because they're the things that come out, or they are produced from the reaction. Okay. Alright, next one. So we need to look at whether or not reactions are balanced. Okay, and this one actually is. So I made a mistake on the last one there, but when we look at a chemical reaction, if the reaction is balanced, it shows conservation of mass. This is a law that matter is conserved in the universe. So no matter what you do to it, the same amount of mass exists before and after. It cannot be created and it cannot be destroyed. So you can't make new matter out of nothing, and you can't make matter disappear and go away. Sometimes we can't see it anymore. It might be a gas, but it's still there. Okay, so just like up here, these little blue and white circles represent elements or atoms, and the fact that they're stuck together means that it's like a compound. So there's these like white circle compounds and blue circle compounds, and they're separated out on this side, but after the reaction you've got the blue circle bonded to white circles. So if you look at how many blue circles there are on the left side, there are 4 blue circles, and on the right side there are also 4 blue circles. So that means that the mass coming from the blue circles was conserved. If you were to count all the white circles, you would see the same thing. There are, I think, 12 if you count them out on the left side, and there are also 12 on the right side because there are 4 molecules with 3 each. So you could count that out, and that would show that mass is conserved from beginning to end of the reaction. The same is true down here. We have this reaction of NaOH, or sodium hydroxide, reacting with HCl, or hydrochloric acid, and it produces NaCl, sodium chloride, and water, H2O. So the reactants and the products, we have to compare them to know whether the reaction is balanced. So if you look at before, we have 1 sodium, we have 1 oxygen, we have actually 2 hydrogens. There's one of them here in NaOH and the other one is in HCl. We have 1 chlorine. So that's the left side. The right side, we have 1 sodium, 1 oxygen over in the water, 2 hydrogens in the water, and 1 chlorine in the NaCl. So before the reaction and after the reaction, we have the same number of each element, and that means that our reaction is balanced, and that means that mass will be conserved. If you are actually doing a reaction and no gases are produced or anything like that, before the reaction and after the reaction, you should actually have exactly the same mass. And so that's what they're showing here, that they have 2 clear liquids, and it weighs 92.95 grams, and afterwards they've poured one of the beakers into the other beaker, and we've got this white precipitate or powder that has formed, and it still weighs 92.95 grams, because in a chemical reaction, mass is always conserved. Okay, moving on. So let's look at types of chemical reactions for real quick. This is the last thing we need to talk about. We've got 5, and the first 2 are synthesis and decomposition. Synthesis is a word that means to make. And so I like to think of baking as an example of synthesis, because you take a lot of different things and you make one thing out of them. Like you take eggs and flour and all that stuff and you make cake. So the same thing is true for the chemical reaction. I have a blue circle and red circle. You react them together and make 1 compound. You could use 2 reactants, or 3 reactants, or 4, it doesn't matter. You could use a lot of different reactants, but basically in the end you're getting 1 compound. So an example is nitrogen gas reacting with hydrogen gas to make NH3. So that's 2 separate compounds reacting to make 1 compound. Synthesis. Decomposition is exactly the opposite. You're starting with 1 thing and it's breaking down into 2 separate things, or 3 separate things, however many. So it's basically just the backwards reaction of what we had up here. That's what I have down here. NH3 breaking down into N2 and H2. And so for the example for this one, I put rotting vegetables, because that's essentially what's happening. All of the molecules inside of the vegetable are breaking down, decomposing. Okay, last 3. So we have single replacement. This is when you have a compound and just an element by itself, and that element replaces somebody from the other reaction. So here we have a new pair where the green one is now with the red one, and the blue guy is kicked out by himself. Okay, so this is kind of like if there's a couple dancing and somebody comes and wants to dance with the girl, and she wants to dance with him too, so they kick out the other guy and he walks away sad. Okay, it's kind of like that. That's called single replacement. So somebody ends up single and somebody was single to begin with. So magnesium and HCl, that's a compound right there because it's got 2 elements. And at the end we get hydrogen, single element, with a compound of magnesium and chlorine. So magnesium basically just kicked hydrogen out. That's called single replacement. Double replacement is when you have 2 couples and the couples are trading partners, And finally, combustion is when you have a carbon-based compound and it reacts with oxygen gas to make carbon dioxide and water. And this is just any kind of burning reaction is combustion. All right, that's it for today.